So, the yesterday's class we were talking about probability distributions, right. We talked about binomial, we talked about Poisson, and then we talked about uniform and normal distributions, and I told you why we do central normal distribution, I mean standard normal, and then I also showed you the table how to look at it, right. So, moving forward, see I mean this is not an undergraduate class where I will delve deeper and deeper into normal distribution. I am expecting you do it, okay. So, do not expect, as I told you, gave you an example problem. So, it will be somewhat tricky and I expect you to go through more about normal distributions, okay. With that note we will proceed. So, as I told you in the last class, towards end the idea is to get a distribution for x bar. Why do I need a distribution for x bar? Only when I kind of understand the distribution of x bar can I talk about confidence. I can talk about, I know that 100% I cannot be sure because that requires n tending to infinity, right. So, that is when I said okay, if I have n equals to 1000 versus n equals to 10,000, what is the difference it makes? That means my sample clinical trial. So, or I can ask another question, what is my value of, what is the sample size if I have to prove my hypothesis or disprove my null hypothesis with 95% confidence. I told you briefly, null hypothesis is something the status quo. So, this drug molecule does not work, okay. I want to, it is a qualitative statement, let us say the average number of times this drug molecule or the probability of this drug molecule working is 50%. Let us say that is what we start, 50% is why we start with 50%, it is like tossing of a coin, right. So, that is too bad, right, 50% you do not need to even predict because it is like random only will give you 50%. So, you start with this null hypothesis. Your alternate hypothesis is what? This drug molecule, the probability of this drug molecule working is 95% or 80%, let us say. You want to disprove this null hypothesis with certain confidence, right. Let us say I want to be 95% sure thus this drug molecule works, performs about 90% or whatever number that is. Now, to do that you need to conduct experiments. Now, the first question I ask is, of course, a lot of confounding factors etc. will be there, but first thing is what is the value of n, the sample size, how do I do about it, right. So, those are the questions that will be answered by knowing the distribution of x bar. Remember, we are always talking about averages, not one sample. So, the key two parameters we will play with is what? X bar and sample mean and sample variance. Yesterday we learned both of them are unbiased estimators, and sample mean also converges to population mean when n tends to infinity. So, on an average when I say that on an average this drug molecule works 90% of the times. You see the statement, we are making it better and better. On an average this molecule works 90% of the time. How much sure about it? I am 95% sure about it, right. This is the kind of answer you would want to give, and everything should be supported with data, right. These are the inferences that one want to give, right. I mean these are the conclusions you would want to see when you are doing a clinical trial, or when you are presenting the investor or the manager will be looking at these claims. What is the claim you are making about this drug molecule as a statistician, right. You say on an average this drug molecule has worked this much percentage, I am confident about this much percentage. Then you have to give the details, or what is the sample size, what are the factors you have considered like age group, preconditions, right, whatever health conditions, what are the, how did you choose the sample size, right. So, these are essential for any industry as well as when you do research as well, right. How do you choose the population, why did you choose it, how many factors you have considered, what is the sample size, why is that sample size you have considered, etc. Okay. That is why clinical trial takes how long, how much time does clinical trial take? Typically 3 to 4 years goes in trials, multiple trials, typical numbers. Okay. So that is why the drug molecule is patent is also for a longer duration. They don't take away the patent just like that. Like COVID, there is still a patent, right? The COVID vaccines, people were asking the embargo should be taken out, etc. I mean, our PM was one who was talking about removing the embargo or removing the patent rights on this, but nobody will do it. It's a huge investment. It's a huge investment to make the drug. Okay. So having said all of that, so we are now interested in sampling distribution of X bar, and that is when, this is the reason, this is one of the reasons, the central limit theorem is one of the reasons why normal distribution or Gaussian distribution is way popular than what we could think. I shortly call it a CLT. Of course, we know what CLT in IITM language is, but the celebrated central limit theorem is the following: if x1 to xn is a random sample of size n taken from a population, okay, so you are taking n samples from a population with mu and finite variance, with mean mu and finite variance sigma square, and if x bar is the sample mean, okay, the limiting form of distribution is standard normal distribution, z equals to x bar minus, why am I doing sigma over root n here in the denominator? Why did I get sigma over root n? What is standard normal? X minus mu by sigma. What is sigma for x bar? Sigma squared for x bar is what? We derived it in the last class. What is sigma squared for x bar? Sigma squared by n, and that is the reason why sigma for x bar is sigma over root n. Okay, this is mu, x bar, expectation of x bar equals to mu, and variance of x bar is, so standard deviation of x bar is sigma over root n. So, and there are catches to it. The population, so what do we do? x1 to xn is taken from an IID population. I told you in the last class what is IID. So of course this x1 to xn is taken from an IID population. N typically is greater than 30 is enough. You do not need infinite samples. Okay. So what are we saying? When you take n samples at random, typically n greater than 30 from a IID population, then x bar follows Gaussian, right? X bar follows Gaussian. So that is a beautiful theorem in the sense, I do not know about the underlying population at all. I do not know about underlying population, but I collect samples from an underlying population, take the mean value follows what distribution? Gaussian, right? I do not even know the underlying population, I do not even need to know what is the underlying population, but I just need to know I just need to take more number of samples, and of course I should make sure that the underlying population is independent. It is not even IID is required, it is not even identical. You can take from multiple distributions provided they are all independent, the samples are independent. If the samples are independent, x1 to xn samples are independent, then x bar follows what? Gaussian. What is x bar? Summation xi by n. So n is a constant. So sum of n independent random variables follows Gaussian distribution. loosely speaking. What am I saying? Sum of n independent random variables where n is greater than 30 follows Gaussian distribution. That is the most powerful theorem, because that tells me I do not care about the population at all. I just take sum of n independent random variables and it follows Gaussian. So tell me the noise, the noise corrupting the temperature in this room, what distribution is it? Suppose I measure temperature in this room. The temperature in this room is affected by noise. What are the noises? What kinds of noise it get affected? Of course, sensor itself has noise, sensor noise, and then our breathing rates, the closing and opening of doors, windows, right? The ambient itself, variations. All of them, are they independent or dependent? Independent. Why do my breathing rate and yours should be same? Is there any relation? Closing and opening of the door versus me breathing? No, not much. So all are independent. Now, when they add up to the noise, what kind of noise is it? Gaussian, right? So this is the reason when you see in literature or when you see in papers, they will simply make one assumption. Noise corrupting the system is assumed to be Gaussian. They will not say why even today, because it is well known that it is because of central limit theorem. Such is the power of this theorem, right? So anywhere you do not have any knowledge and you assume that the underlying system is IID, you will say, yeah, x bar follows Gaussian, sum of n independent random variables follow Gaussian. Okay, so that is why this Gaussian distribution is very, very popular. Why do you expect a triangle? Okay, mathematically, this is not a math course to prove, but I can tell you the whole idea. Okay, so how do I characterize a PDF? How do I characterize a probability distribution function? If I want to characterize mean and variance alone, not necessarily. Mean, variance, kurtosis, skewness, and there are several factors, right? X minus mu per 3, mu per 4, mu per 5, etc. So we call this as moments. We call this as moments of a distribution. Okay, x minus mu, mu and x minus mu the whole square is first and second order moments, a zeroth and second order moments. Okay, we have third order moment which is x minus, which is skewness. Fourth order moment is kurtosis. Like that you have nth order moments you could generate, and there is something called as a moment generating function, MGF. Okay, which is called as moment generating function. Okay, so it is an equation which generates various moments for various periods. Now this, under these assumptions, okay, you can prove that the moment generating function of x bar is equal to the moment generating function of normal distribution. Okay, so moment generating function is typically an exponential function with lambda, etc. Okay, and if you did yesterday's class, probability distribution binomial to Poisson, how did they do? Okay, how did you get the E exponential? That is the key. Okay, so it was combination actually, NCX p to the power x, q to the power n minus x, changing to exponential by a property, right? That is the idea. And if you notice, binomial distribution is what? IID. Okay, that is converted to exponentials. And what is the distribution of Gaussian distribution? What function does it have? Exponential. So you understand that. So the moment generating function of a x bar can be mapped to moment generating function of our Gaussian under the conditions that x1 to xn are independent. IID is precise. Okay, IID is what the proof is, but then later on people have relaxed that identical but it should be independent. Okay. In fact, this has a long, this don't assume this theorem is, this is very naive. Okay, this is very powerful. It may appear very simple. So stock markets in 2008 crashed, everybody knew it, right? Subprime debt crisis. Okay, it's a CDOs, collateral debt obligations. Okay, it happened in 2008. Okay, so one of the faculties from Columbia University was also involved, where I did my postdoc. Okay, he was also involved big time. Columbia is very well known for, university is well known for economics. Okay, most of the Nobel laureates in economics are from Columbia. So the main assumptions in the stock market, by the way, what is the input to a stock market when you want to model a stock price? Buyers and sellers, that's all. What is the input to a stock market? What is input to EEG? I am telling you for a reason. Okay, what is your input to EEG? What is your input to EEG? Huh? I didn't get you, Avantika. Input to EEG, electrical activity, that's output. What is your input? Huh? Signals are what signals? Is that all? Only nerve action potential will trigger EEG. So you don't do anything, EEG doesn't exist. When you sleep also EEG is there. So what is the input to EEG? Can you even, what is the input to ECG? Your heart activity, what is the input? Huh? So as biomedical engineers, don't underestimate yourself that you are only in one field, like biomedical, and then only in research. You have a lot of potential outside. You learn techniques which are across, cutting across domains. Okay. What is the input to ECG? ECG, pacemaker. Is it the input? Pacemaker is an input, pacemaker is a system. What is the input to ECG? EEG, ECG, EMG, ERG, EOG, whatever, MEG, MRI, what are the inputs? You cannot tell what is the input at all. There are so many inputs. The moment I think, things will change in my EEG pattern, right? So what is input? There are too many things that are influencing the output, that it is better considered there is no input at all. Okay. So what do we think? We don't consider, when we model it, we model there is a fictitious input to the system. What is the fictitious input? Because this is affected by too many quantities. So what is the best to assume? What is the input you assume? Somebody? What random? White noise, IID. There are too many things which are influencing your system. So what is the input? If you ask me what is the input to an EEG, I will simply say there are too many inputs. It is better assumed that as all of them are independent. So it is a white noise. IID. No, not same. White noise is IID, that's all. I didn't say Gaussian. You understand? Simple as it is. Now, related with stock markets. What is the input to stock markets? Today, somebody doesn't, today our Prime Minister says something, stock markets will fluctuate. Not just our Prime Minister. In anywhere in globe, any geopolitical tension will result in, will influence. War stops in Russia, stock markets will cheer. Somebody joins the war, stock market will go down. Oil prices, somebody coughs in Dubai, oil prices will shoot up. Everything will change, right? So it is like exactly like our body biosignals. So there is nothing different between a biosignal and a stock market in terms of analysis. They are both time series to me, right? And that's when whatever techniques you learn, you can do that there as well. Okay. So coming back, the input is considered to be a white noise, IID, and most of the time they assume it also Gaussian. because again sum of n independent random variables is Gaussian, right. This was the assumption made in 2008 during this lending crisis. When they modeled it, they said the stock markets are healthy, I mean the debt markets are healthy, but what is missed out is there are voluntary players, okay, there are voluntary players who have induced a dependency effect. Ideally it should have been independent, right. Ideally there are too many things which influence and they are independent. So your model is based on the idea that it is all independent. Now there are some players who have introduced some kind of input which is a correlated effect. So all the models broke down, okay, and nobody was able to watch it out. And later on many papers after the crisis were retracted. Many economics journals paper were retracted and they started reconsidering whether we should even think independent input as a good idea to model. So now it is under the general impression that you do not think of independent input as a case, because many a times our inputs can also be correlated, and therefore you have to consider different kind of models, okay. So till 2008 and even today many stock markets everywhere they consider input to be IID Gaussian. They also add Gaussian because sum of n independent random variables is what? Gaussian, okay. So you will see this assumption everywhere, okay, not just in one domain, biomedical domain, across domains. And I tell you, don't restrict yourself biomedical engineers like I should be doing only EEG. Whatever you do in EEG, ECG is what cutting edges. You can do the same thing in wall sheet data as well. I have played there as well, it is the same. The jargons differ but the ideas are simple.